let us look at a couple of examples for central limit theorem. So in this example, they are looking at the radiation level on reclaimed land. So suppose that the radiation level for the reclaimed land has a distribution with a mean mu 5.0 working levels and a standard deviation of 0.5 working levels. So that means that if you take the x to be the radiation level, the mean of x is 5 and the standard deviation of x sigma is 0.5. So suppose that 20 houses built on this reclaimed land are randomly selected and the radiation levels measured in each. What's the probability, approximate probability, that the sample mean for these 20 houses exceed 5.2 working level? So in other words, so it's basically you pull a, say this is the probability distribution according to this question, that even though they give you the mean and the sigma, so nothing, we don't know anything about the probability distribution of x. So it could be anything. So so what you're doing is that you pull a random sample of size 20 out of it, and then you want to figure out the probability sample mean for these 20 houses exceed. So which means that when you say sample mean for that sample, so the average, that this is sample mean for those 20 houses, mean this is referring to the x bar. So so for those 20 houses will exceed 5.2. That's what you want to figure out. So so we cannot basically do this question unless we know anything about basically unless we have a big sample, because the central limit theorem says that x bar average will follow a normal distribution but for the large n. So the question is now this 20. That is, according to what we said before, it's not quite large actually, okay? But there's no any other way we can do it. So we're going to use the central limit theorem anyway, but the answer you are going to get is not really, you cannot rely on too much because that your sample size is not that large. Unless you know that this curve is a smooth curve, the symmetric type curve, normal curve, then it is different story. So in that case you don't need the large n, okay? So in other words, if this is normal curve already, then n could be anything. So now, so I'm going to apply the central limit theorem anyway, even though that 20 is not big. So this, according to the central limit theorem, so has a normal, this is x bar is normally distributed with a mean, the same mean 5, but the standard deviation of x bar curve is going to be the original standard deviation sigma divided by square root of n, which is 0.5 divided by square root of n, so that is going to be 0.1118, okay? So in other words, for the x bar curve, the mean is 5, the standard deviation is that. So now we want this probability. So since we already know that this is going to follow a normal curve, so you convert into this one into z and then read the z table. So here this one, so to convert this into z, so you need to this thing minus mu, which is 5.0, divided by the standard deviation. So minus 5 from this side, minus 5 divided by the standard deviation right there. So do the same thing for this side as well. So it's going to be, this is the z greater than, this part is 1.79. So it's after that it's a matter of reading the z table. So this is the z table, so you want this area. So read the z table to get that area. So which is going to be 0.0367. Okay, so here the thing is that this is not very large, so answer is going to be somewhat closer to that, but you don't know exactly, okay? It's larger than, better the approximation. So it's going to be somewhat close, but it would have been better. This is like around 30, 40, something like that. Okay. So part B, what if n equal 4? Can you answer the question in this part A? The, the, the answer is no, unless you know about the distribution of that. Unless this distribution is a normal curve, then the other theorem, okay? So then if it is a normal, this is going to be normal. So regardless of the sample size. So in other words, you can answer this one only if the initial population, which means that, is a normal curve. So if that is normal, so everything is exactly work out exactly the same way, okay? So then the x bar, so it's going to be, so x bar curve is going to be this way, x bar curve, normal with 5, and the standard deviation is going to be 0.5 divided by square root of 4 now. So that is going to be the standard deviation for that, for the curve. So now once you get to that, so this is going, this thing minus 5 divided by that, which is that. So this is going to be 0.8. So the probability is z more than 0.8. From the z table, read the z table to get that. This is going to be 0.2119. Okay, so you can answer this question only if this initial population is a normal curve. So that's the first part of that central limit theorem. Okay, so yeah. All right. So anyway, so that's that. Okay, so the next example. So the next example, the weight of food packed in a certain container is a random variable with a mean weight of 16 ounces and a standard deviation of 0.6 ounces. If the containers are shipped in boxes of 36, so find the approximate probability that randomly picked box will weigh over 585 ounces. So in other words, this is like a small, like a soda can or something like that, okay? So the weight of each container, so these are 16 ounces. So if you take that, the mean of that is going to be 16 ounces and the standard deviation is 0.6. But they're packed on this kind of a big box. Each box has a 36 cans in that. So according to this question, the distribution of that you do not know, even though you know this mean and the standard deviation. So the distribution of x could be something like that. But so we want to find the probability. If you pick a big box like that, the total weight of that big box is going to be, which is that x1 plus x2 x36 is going to weigh over 585 ounces. So here, so to get the x bar, so that way you can apply the central limit theorem. So this one, using that summation notation, sigma xi. Okay, I'm sure you are familiar with this sigma notation in your prerequisite class, sigma, which is the sum. So you divide both sides by 36, so that way this will be x bar right there, and 585 divided by 36, which is that. So according to the central limit theorem, for large n, x bar is normally distributed with 16 that, and standard deviation, this standard deviation divided by square root of 36, which is going to be 0.1. So now, so you apply this normal curve to get this probability x bar greater than 16.25. So convert this into z. When you convert this into z, you this thing minus 16 divided by this standard deviation. Okay, so 6 that, so it's going to be the probability z more than 2.5. From the z curve you need to get that. This is the z curve. From the z curve you need to get the area, this area. Find from the z curve is going to be 0.0062. All right, so the thing is that this 36 is quite large actually. So way over, kind of over 36. So the part B, if the containers are shipped in boxes of 12. So in other words, so 12, so can you answer this question? So the same way, but the only thing is that now n is 12, which is not large. So you can answer this question only if that initial population, which is I'm referring to this is a normal curve. Okay, so if that is a normal curve, then this part is automatically normal. If x is normal, this is automatically normal for any n. Okay, so then so here this is going to be that. We want to figure out this probability that sigma xi more than 190 ounces. Okay, so here, so this is correct for any n. So this one, divide both sides by n, which is 12 to get x bar. So it's that 190 divided by 12 is going to be 15.833, and convert this one into z, this thing minus 16 divided by this value. Okay, so then that will give you that z more than that. The answer is once you get to that, read the z table. So it's 0.8315. So okay,